Ugh. Welcome to a week 4 problem solving session for the course Introduction to Information Theory on NPTEL. I'm your recitation instructor Sachin from the Indian Institute of Science. Today, as usual, we'll be solving 10 multiple choice questions based on the topics covered in this week's lectures, which is Lempel-Zev algorithm 77 and Lempel-Zev-Welch algorithm. We'll start with questions based on LZ77. Following bits 100, 1010, 0001, 0001, 111, 001, 01001, 01, followed by 5 zeros, were encoded using LZ77 algorithm with sliding window size 12. So we'll use this setting for first three questions, Q1 to Q3. Q1 is what is the initial entry in the dictionary? And the options are 12 zeros, 12 ones, or 11000, 100, 0101, or none of the above. So this is the LZ77 algorithm, and for LZ77 algorithm, initial dictionary contains first NW symbols. Here NW is 12, so initial dictionary is the first 12 symbols of the sequence that we want to encode. So it is the first 12 symbols are 1010, 0001, 0001, which does not match with any of the first three options, so the answer is none of the above. The second question is for the same input sequence or the source sequence, what is with the same sliding window, what is the initial code word? And the options are again, first option is 12 zeros, second option is 110, 001, 000, 101, third option is 111, 111, 111, 111, and option D is none of the above. So in LZ77 algorithm, the initial entry in the dictionary is the first NW bits in the sequence to be encoded. And the first code word is also the first NW bits in the sequence to be encoded. So it is equal to the initial dictionary entry. So the first code word is again this thing 1010 0001 0001. So in LZ77, the first code word C0 is the same as the initial dictionary. So C0 is this part, which does not match with any of the first three options. So the answer again is option D, none of the above. The third question is for the same input sequence, for the source sequence, and the same sliding window. What is the list of subsequent code words? Li, mi is options are 30577430. Option B is 10214954342110. Option C is 10214954392110. Option D is none of the above. So here, since it's a multiple choice question, once you start write, writing the code word using the algorithm, as soon as you get C1, the first code word, you will know whether uh, it's any of the options or not. So from C1 you can, sorry, give me a minute. I have a parcel I have to take. Alright, where was I? So since it's a multiple choice question, you can tell within, you can just match your answer at each stage with the options, and at some point, if none of the options match, you will know it's none of the above. You might not need to solve the entire thing, but just for your understanding, I'll do the entire algorithm for this example. So here's the way you apply the algorithm. First, you have to note that the sliding window is 12. Let me also copy down the sequence. This is the source sequence that you need to encode. This is the ith iteration where you find the dictionary entry, the matchings, ith matching substring, the length of the ith matching substring, the index of the ith matching substring, and the code word. For I equals 0, there's no dictionary entry. Prior code word is 11000, the first 12 bits. Uh, Sorry, I think the solution manual and the assignment itself are not matching for whatever I've been given. So this solution is, I'll have to write my own solution. Let me do the algorithm anyway. Just that, sorry, I'll be right back. I have a parcel. Okay, I'm back. Let's see. Now the initial code word is the first 12 bits. It's 1010 000 1 000 1. Stops here. All right. Uh, First code word for the first matching substring. The code word, the dictionary now is just 1010 000 1 and the first symbol in the leftover part is 1, and there are one, two, three, four locations where it matches. Then 1 1, so it doesn't, this location doesn't match here, doesn't match here, but this 1 1 does match with this 1 1 1 1. Again, this 1 1 1 matches with this 1 1 1 1 1 1 0. So there's no match for 1 1 1 0. So 1 1 1 matches with a substring that starts in your dictionary. So it starts in your dictionary 111. So the matching substring is 111. Length of the matching substring is 3. The position where it starts. There are two ways to do this. What is done in the lecture is you write P is the position from the left. And you start with 1, 2, 3, 4, 5 up to this is 12th position, and then M is N minus P, which is 12 minus 12, 0, uh, which is the same as which is the same as starting from the rightmost end, but starting with 0. So now this is the 0th position, and that is exactly MI. So M1 is 0. Now the code word is 30. For the second code word, you have to update your dictionary by removing L1 bits from the beginning of the dictionary. So you're removing the first 3 bits, 101. So starting out with 00, 001, 0001, and adding the matching substring, which is 111. Now you have moved your dictionary by slide. It's like a sliding window. So this is your main dictionary, and you have to start finding matching substrings from this location, which has a 0, which matches with this 0 and this 0, two matching locations. Then substring of length 200, does it match anywhere in the dictionary? It matches here, and so substring of length 10, there were many matching places actually. This, all these were matching with 0. Substring of length 2, which is 00, Now 00 doesn't match in too many places, but still you could start here and get 00 here, 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 and you would get, if you start from those positions, you would get 00. Substring of length 3001, does it match anywhere? So here it's 000, from here it's 000, from here it's 001. So you have that. So if you start from here, you get a matching substring. Similarly, you could have started here to get a matching substring. So we'll have to check one more length, a substring of length 40010. You have that anywhere. So you don't have 0010 if you start from there, but you do have 0010 if you start from that position. 0010. These two match. So the matching substring of largest length is 0010. Its length is 4. Starts at the position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 4, 9. Now you have to update your dictionary by removing the first 4 bits. So 100011. And you have to add the substring 0010 to it. Now we are at, now your dictionary is this part. Let's start the procedure again. So 1, you have a match in all these places. 1, 0. You have a match. Start here, or here. 1 0 0 0. You have a match if you start here. 1 0 0. Sorry, start here, but not if you start here. So that's ruled out. 1 0 0 1. So you can't start here. That's 1 0 0 0. This is 1 0 0 1. Okay, can start here. 1 0 0 1 0. 1 0 0 1 0. You do have that. 1 0 0 1 0 1. 1 0 0 1 0. You do have that. 1 0 0 1 0 1 0. 1 0 0 1 0 1 0. You have that. 1 0 0 1 0 1 0 1 0 You have that too. 1 0 0 1 0 1 0 0. No, you don't have that. You get 100, 10, 100. So it's a matching substring of length 1, 2, 3, 4, 5, 6, 7, 8. It's 100, 100, and it starts at location 0, 1, 2, 3, 4. So the code word is 84. Now you have to remove 8 bits from your dictionary. 1, 2, 3, 4, 5, 6, 7, 8. So your new dictionary starts from here. You have to append 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. Your new dictionary ends here. So for the fourth code word, your dictionary is 0010 100 10100. Substring, do you have a 000 anywhere? So we do have, if you start from here, 000, which matches with the leftover substring. So final substring is 000, which matches, length is 3, and starting position is 0, 1. Or you could start from here. That's also a matching substring. So you could start from the 0 place, and we would like to have the smallest value fm. So this is actually 0. And with that, you have encoded your entire sequence. Therefore, your code word coded sequence is C0 is 1010 triple zero one triple zero one, followed by 30498430, which doesn't doesn't match with any of the options. It's close to this. So according to the solutions that have been given, it was option A. So I think they started off with a different sequence. So, but the sequence given here in this question is different. So the answer turns out to be none of the above. I think they've got different year uh, questions and answers mixed up. But the procedure is the same. So the answer is option D. Hello. Second floor. Let's move on to the next question. Question 4. Comma free encoding of 43 is given by. Options are 00, 111, Option B is 0010 111 001. Option C is 0011 Option D is none of the above. Here is the solution. For a positive integer k with binary representation, b of k, which requires cardinality of b of k is equal to log of k plus 1 base 2 ceiling number of bits. So to represent 4 in binary, it would be 100, which needs log of 4 plus 1, ceiling of log of 4 plus 1, which is ceiling of some 2 point something, just 3. That is, you need 3 bits to encode the number 4. You need 3 bits to encode number 5, 6, 7. Then for 8, you need 4 bits. So modulus of b of k is the number of bits you need to encode the number k. B of k is the binary representation of the number k. K is in decimal. B of k is the binary representation. Modulus of B of k is the number of bits in the binary representation of k. With this notation, the comma free encoding comma free encoding is given by E of k is E hat of B of k concatenated with B of k, where E hat of B of k or E hat of a number p is U of mod of B of p concatenated with B of p, where U of n is 0 n minus 1 times followed by 1. So for k is equal to 43, B of k is how much? Get 32 ones, and you don't need a 16. You add an 8, that's 40. You don't need a 4. You add a 2, that's 42. You add 1, that's 43. Plus 1 plus 2, 3 plus 8, 11 plus 32, 43. And the number of bits you needed to do this is 6. So E of 43 is E hat of 6 concatenated with 101011. So right from that you can kind of rule out option B and C, because it has to, the comma free encoding of 43 has to end with the binary representation of 43, which is 101011. There's only two in option A, so it should be either A or none of the above. Next, E hat of 6 is, for that you have to find B of 6. Binary representation of 6 is 110. Modulus of B of 6 is 3. So E hat of 6 is U of 3 concatenated to 110. U of 3 is 001. Therefore, E of 43 is 001 110 101011, which is option A. Question 5. List of noise-free code words received at the LZ77 decoder that uses a sliding window of length NW equals 12 is given by 1010 1010 0001 4055. What is the input binary sequence that was encoded using LZ77 algorithm with NW equals 12. Options are 1010, 1010, 0001, 1110, 10101. Option B is 10101010 0001 and 4 1s 0 4 1s. So C is 1 followed by 4 zeros 1010 10 10. Option D is none of the above. Solution is as follows. First code word is always the first NW bits of the source sequence. So right from that we can rule out option C because it does not match with the first NW bits of option C. It does not match with the first code word. Next code word is 40. So 101010100001. L1 is 4, M1 is 0. So the string starts matching from the 0th position and it matches for 4 bits. So if it starts matching at 0th position, which is this position, it matches to the first bit, so it should be 1. Then it matches in both these positions, so first 2 bits should be 1 1. Matches in first 3 positions, so the first 3 bits must be 1 1 1. Matches in first 4 positions, so the first 4 bits must be 1 1 1 1. So in this way, you have a substring 1 1 1 1 which matches with another substring 1 1 1 1 that starts within your dictionary and its length is 4. Now next you have to slide the dictionary to here, eliminate first 4 bits. Now L2 is 5 and M2 is 5. So the next 5 bits match with the substring 5-bit substring in the dictionary that starts at position M2 is equal to 5, which is now you start from here. This is 0 1 2 3 4 5. So the starting position is this is M2 and your source sequence matches with 5 letters starting from there, 5 bits starting from there. So it's 0 1 1 1 1. Which is 0 1 1 1 1. That matches with. So now the Input sequence must be 1010, 1010, 0001, 1111, 01111, which is option B. Question 5. List of noise-free code words received at the LZ77 decoder that uses a sliding window of length NW equals 12 is given by 1010, 1010, 0001. Sorry, that was the previous question. We are at question 6 now. A binary sequence is encoded using LZ77, sliding window 8. The code word of length Li were encoded using comma-free encoding and Mi represented using binary representation of the number. The encoded sequence is given by 100101100, 1111111, 0101, 101011, 001111, 01001. List of code words is given by option A 100, 10110, 752651, 100, 10110, 756251, 100 1010110 576251. None of the above. The encoded sequence is this. C0 is first NW, which is 8 bits. So 100 10110. So that is C0. Next we have 01. So next two bits are, since 01 has a single 0 in it, the length of the representation of the length of L. The length of L is represented by the next two bits, which is 1 1. So the length of L is 1 1, which is 3. So the next three bits represent L 1 1 1. And for M we use log of NW base 2 is 3. So 3 bits for M. That means up to there is L1, this is M1. L1, this is M1. L1 is 7, M1 is 5. Next you have 0 1, which means next two bits represent the length of L. So 1 0 represents the length of L. That is 2 is the length of L. So L is 1 0. L2 is 2. M2 is 110, which is 6. So from that you can eliminate options B, C already. Left over is only option A or none of the above. Next you have 0 1, which has a single 1. So the next two bits represent the length of L. So 1 1 represents the length of L. So that is 3. So the next three bits represent the length of L. Next three bits represent L. So that is 101. So L2 is 5, L3 is 5, M3 is the last three bits, which is 001, which is 1. So L3, M3. Therefore, the code words are 1001011075251. 2651, which is option A. Question 7. A ternary sequence 11012211234567 8 111111 11 and 2010220201. That's the sequence is encoded using LZW algorithm. The encoded sequence is given by options are 110, 133, 4, 10, 10, 7, 6, 1, 8, 15, 6. B is 110, 1, 3, 3, 4, 10, 11, 3, 6, 1, 8, 15, 6. Option C is 2, 2, 1, 2, 3, 3, 4, 10, 11, 7, 6, 1, 8, 15, 6. Option D is none of the above. The LZW algorithm goes as follows. You have your sequence. You have to write down the phrase and the index. Initialize with phrases of length 1. 0 is indexed as 1. 1 is indexed as 2. And 1 is encoded as 1, which is the index of 1 is 2. Then 1 1 is not a phrase in our dictionary, so you have to include 1 1 as a phrase in your dictionary with index 3. Next, you have to encode second one as 2. Then 1 0 is not a phrase in our dictionary, we have to add 1 0 as a phrase with index 4. Next, 0 you have to encode by index 1. 0 1 is not a phrase in our dictionary, so 0 1 has to be included. Index 5. Then you have to encode 1 as 2. Then 1 2 is not a phrase, so you have to add 1 2 as the sixth phrase. And 2 is not, sorry, this was ternary, so there were actually three possible input symbols. So indexing was actually 0 1 2, and 2 is the third index, so all these have to be shifted by 1. 4, 5, 6, 7. Then next we have to encode 2, which is index. So 2 is actually indexed. The code word for 2 is actually 3. Then 2 is not a phrase, so I have to include that with index 8. Then I have to encode this 2 as 3 to 1 is not a phrase, so I have to include that as ninth phrase. Then you have to encode 1, but you have 1 1 as a phrase, so you can encode 1 1 as 4. And 1 1 1 is not a phrase, so I have to include that. Next, starting from here, you can encode next 3 bits 1 1 1 from the as the code word 10, but the 4 bits 1 1 1 1 are not a phrase, so you have to include 1 1 1 1 as 11th phrase. Now 1 1 1 1 can be indexed as expressed as code word 11, and 1 1 1 1 1 would be code word number 12. Now you have 1 2, it's code word number 7. 120 is not in the code book, so 120 is included as the 13th code word. And 01, the 6th code word. 010 is included as the 14th code word. Don't have 02, so 0 is again just code word 1, and you have to include 02 as the next code word. So the 02 is the 15th code word. Then you have 22. Again, 22 is not a code word, so you have to include that as a code word and encode 2 as index 3. Oops. 22 is actually a code word, so you don't have to include it again. 22 was already included as code word number 8 here. So instead of encoding only 2 here, you can encode 22. So code word number 8. 220 is not a code word, so you have to include that as a 16th code word. Then 02 is the 15th code word. 020 is not in the code word, so you have to add 020 as the 17th code word. 01 is code word number 6. So by the LZW algorithm, the encoded sequence is 2212 334 10 11 76 which matches with option C. Right. Question 8. In question 7, if the dictionary can only save 12 entries and the dictionary is not updated after it is full, what is the coded sequence? Two two one two 334 10 11 76 18136 1101 334 10 10 76 18136 110 133 410 11 36 18 136. Or D, none of the above. So the dictionary contains only 12 code words. That means it only goes up to here. So the earlier parts of the sequence are fine up to adding one 1 1 1 1 1 1 at which point you are here. Let me copy the sequence. So up to this point, same as Q7 up to this point. So it's 2 2 1 2 3 3 4 10 11. Then you add the code word 1 1 1 1 1. Then you have to start encoding from 1 to 0 this part. So again you encode 1 2 as code word number 7. Now if you had more dictionary space you could have added 1 to 0 as your code word number 13. But as we have done here, but since you don't have dictionary space and you don't update the dictionary anymore, that's it. This is your dictionary. So you encode 1 2 as 7 and 0 1 as 6, then 0 2 as there's no code word, 0 as index 1, 2 2 as index 8, 0 as index 1, 2 0 as 0 2 0, 2 as index 3, and 0 1 as index 6. So that matches with option A. Ninth question, a ternary source is encoded using LZW algorithm. ABC are respectively the first three entries in the dictionary. The received noiseless code sequence is 12435811011. What is the source sequence? Is it AB, AB, C, BAC, ABA, BA, BC? Is it AB, AB, CBA, BAC, AA, AAA, B? Is it ABA, BCB, ABA, BAA, AA, or is it none of the above? So the dictionary and the code word I'll write down on the left side. You have A, B, C are code words 1, 2, 3. Received sequences 1, 2, 4, 3, 5, 8, 1, 10, 11. If you receive 1, you should have received A. Then you received 2, it should have been B. First bit of this second received vector, there's the innovation symbol for the previous phrase. So AB must be code word 4. Then you received 4, which is AB. The first symbol of that as A is the innovation symbol of the previous phrase. So BA is the next code word. Then you received 3, which is C. So ABC is the next code word. 6. So 5, which is BA. First symbol is B in BA, which is the innovation symbol for the previous phrase C. So CB is the seventh code word. 8. So you don't have 8 yet. That means as soon as the code word was formed, it was used in the LZW algorithm. But we know that uh, first symbol of 8 is the innovation symbol for the previous phrase BA. So the 8th code word actually started out with the previous phrase BA and the first symbol of the 8th code word, which is actually B. So BAB is the 8th code word. Then you received 1, which is A. BA is the ninth code word. Received 10. So A is the 10th code word. Why is that? That's because the first letter of the 10th code word is the inversion symbol for the previous phrase, which is 1, which is A. So the 10th code word is A followed by the first symbol of 10th code word, which is A. Kind of a self-referential thing. Then 11 was transmitted. Again, it's A. That's it. And that matches with which option? AB, CBA, BAB. I think it's option C. Final question is a ternary sequence is encoded using LZW algorithm. The coded sequence is given by 2212 334 1011 103. If A, B, and C are the first three entries in the dictionary, what is the decoded sequence? Options are BBAB, CC, ABA, BBB, AA, CCB, or BBAB, CCBB, BBBB, finally C, or BBAB, CCBB, BCCC, BACBC, or none of the above. And the solution is Again, we'll write the dictionary code word 22, 1, 2, 3, 4, 10, 11, 10, 3. A, B, C are the code words 1, 2, 3. So we received 2, which is B, then again B, code word BB, then A, code word BA, then B, code word AB, then C, BC, then again C, code word is CC, then BB, code word is CB, then 10 is BBB, 11 is BBBB, 12th code word is. Then you received BBB, so 12th code is 5Bs, and then you received third code is C, so BBBC is 13th code. So decoded sequence is BB, AB, CC, BB, 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 BBC, which is option B. Sorry, is it option B? BB, BBB, BBBB. No, it's not. It's not any of the options. There must be 12 B's. Here there's only 1, 2, 3, 4, 5, 6, 7, 8, 10. So there must have been 2 more B's. Then it would have been option B. Now this sequence matches with none of the options. So the answer is none of the above. And with that, we have completed week 4 problem solving session on Lempel-Ziv 77 and Lempel-Ziv-Welch algorithms for universal source compression. I will see you in the next week with problems from the lecture videos released this week for week 5.